Today on AI Paper Podcasts, we're looking at a paper called ACoT-VLA, Action Chain of Thought for Vision Language Action Models. It's from Linking Zhang and a team from Beihang University and Agibot.
And this one is really tackling what they call the Semantic-Kinematic Gap in VLA models. So the core problem is that models like OpenVLA, they think in language or in images.
Which are just proxies, right? They're not the actual movements.
Exactly. They're indirect. So the solution here is this action chain of thought, or ACoT. Instead of the model predicting text as its reasoning, it predicts a rough sequence of actions first, like a draft of the trajectory.
Okay, a draft. And then it refines it.
Right. The architecture has this dual pathway system. There's an Explicit Action Reasoner, the ER, which generates a reference path, and then an Implicit Action Reasoner, IAR, that digs into the vision language model's own cache to find hidden clues about the action.
And the results really speak for themselves. They hit state-of-the-art with 98.5% on the LIBERO benchmark.
Which is huge. It surpasses strong baselines like Pi 0.5 and OpenVLA, and it does especially well on robustness tests. It's a really compelling idea, moving the reasoning out of text and into the action space itself.
Okay, so that's the 1-minute summary for everyone busy building these things. Now, let's actually, break this down, because if you follow the VLA space vision language action chain of thought, almost always means you're letting the LLM talk to itself in text.
Right, and that's been incredibly successful for, say, coding problems or math. The model writes out its steps in English, which helps guide its own logic.
But the argument in this paper is that for robotics, that whole paradigm, it just hits a wall. The Semantic-Kinematic Gap.
It's a great name for it.
It really is. It's basically a fancy way of saying that knowing the word grasp is a totally different thing from knowing how to coordinate your motors and fingers to actually do it.
Precisely. I mean, let's look at the current landscape. You have these big models, OpenVLA, the Pi 0 family, and they generally work by taking a pre-trained VLM, you feed it an image, you give it a text command like, put the red block on the green plate.
And inside its digital brain, it's reasoning with text tokens. It might think, okay, I see the red block, I need to pick it up.
Correct. But that's the exact problem. Language is, as they say, semantically rich but kinematically poor. The token pickup is an abstraction. It's a shortcut.
It compresses a huge amount of physical information like joint angles, torque, velocity into just a couple of characters.
And when the model tries to decompress that, to go from that abstract token to low-level motor commands, information just gets lost. There's a gap.
It's like trying to learn brain surgery by just reading a textbook. You get the concept, you know what an incision is, but your hands have zero muscle memory for the scalpel.
That's a perfect analogy. And the other main approach that people use is visual, so things like world models or video prediction.
Right. Instead of words, it predicts what the world will look like after the action, a goal image.
Which feels a little closer to the problem, doesn't it? Thinking in pixels seems more direct for a robot than thinking in words.
Yeah, it does.
But it's still indirect. Thinking in pixels is not the same as thinking in joints. A final image of a block on a plate doesn't actually tell you the best trajectory to get there. It doesn't tell you how to avoid knocking something over on the way.
It's the destination, not the journey.
Exactly. So the core hypothesis of this paper is that to really bridge that gap, the reasoning process itself, it has to happen in the action space. The chain of thought needs to be a chain of movements.
A chain of movements. I like that. The intermediate steps aren't sentences. They're like, rough sketches of the motion.
That's it. So let's get under the hood of the architecture. This ACoT-VLA, they're not starting from scratch, right? They're still using a VLM backbone.
Yeah, Siglet for vision and Gemma 2B for the LMM. You still need that part.
Of course, you absolutely need the semantic understanding. You have to know what a red block is in the first place. But they bolt on these two new reasoners specifically for the action part.
Okay, so let's start with the first one, the Explicit Action Reasoner, or ER. This sounds like the conscious planner.
You can think of it that way. The ER is a pretty lightweight transformer module. Its whole job is to generate that rough draft of the movement we talked about. They call it the explicit action guidance.
The paper gets specific here and says they use flow matching. For the more technical listeners, why that? Why not just a simple, regression head?
That's a really key detail. A simple regression would tend to just average out possibilities. So if there's two good ways to go, left or right, regression might just output the middle path, which could be straight into an obstacle.
I see.
Flow matching, which is sort of a cousin to diffusion models, lets the model learn a whole vector field. It learns how to push any noisy random action towards a valid trajectory.
So it's a denoising process. It takes garbage input and cleans it up into a coherent but still coarse motion plan.
Exactly. The analogy they use, which I think is great, is like a golfer taking a practice swing.
Mm-hmm.
They're not hitting the ball yet. They're just tracing the path through the air to get the kinematics right. That's the ER. It's creating a motion plan.
Okay, so that's the explicit path, the practice swing. But then there's the second part, which I thought was really clever, the Implicit Action Reasoner, the IAR.
Yeah, this is where they get really creative with the VLM's internals. The IAR works directly on the key value cache of the language model.
Which is wild. I mean, we usually just think of the KV cache as this temporary scratch pad for the LLM when it's generating text. How are they using it for motion?
The authors argue that even though the VLM was only trained on static images and text from the web, its deep layers still encode what they call action priors or affordances.
So when the model sees an image of a mug, even if it doesn't say the word grasp, somewhere in its activations, the patterns related to grasping are firing off.
In a high-dimensional way, yes. The concept of mug is right next to the concept of clamping your hand in its vector space. The IRR uses a learnable query and cross-attention to basically mine this cache. It's asking the VLM subconscious, what's the vibe of this action?
Is it a precision task? Does it need force?
Exactly. And they have to downsample that cache, of course. Otherwise, the computation would just explode.
Right. So you get these implicit behavioral priors. So we've got the ERR giving us a geometric rough draft and the IRR giving us the latent semantic vibe. What's next? The action-guided prediction.
This is where it all comes together, the final action head. It takes the noisy action input and treats it like a query in an attention mechanism. And it uses what they call dual cross attention.
So it pays attention to both things separately.
Separately. It looks at the trajectory from the ER and it looks at the priors from the IRR. It's like listening to two different advisors. One says, here's the path, and the other says, and here's the general feeling of how you should move.
And then it just fuses them.
It concatenates the results and runs them through self-attention to produce the final, precise, 10-step action chunk. It turns the sketch and the intuition into a concrete executable command.
It sounds incredibly robust as an architecture, but I got to ask about training. These kinds of multi-part systems can be a nightmare to get to converge.
They can be. They use a flow-matching mean-squared error loss. And they calculate that loss on both the explicit reasoner, so asking, was your practice swing any good? And on the final output. But the secret sauce is teacher forcing.
Ah, right. You stabilize the toddler before you let them run on their own.
That's a great way to put it. During training, you feed the ER the ground truth reference trajectories. You force it to learn what a good rough draft looks like. If you let it guess randomly at the start, the final head would just be learning from garbage.
And the whole system would fall apart. But then at inference time, when you're actually running the robot, you don't have that ground truth.
Correct. So you switch it to self-conditioned mode. The ER generates its own reference trajectory, and the rest of the model uses that as its guide. It's a very standard, very effective way to go from supervised training to autonomous execution.
Let's talk numbers, because a cool architecture is one thing, but can it actually perform? They tested this on the LIBERO benchmark.
And the results are, frankly, staggering. On the overall LIBERO suite, ACoT-VLA gets a 98.5% average success rate.
98.5. I mean, that's basically a solved benchmark at that point.
It's exceptionally high. For context, a really strong baseline, P0.5, gets 96.9. OpenVLA is way down at 76.5.
Wow, that gap between it and OpenVLA is massive. It really shows the limits of that standard approach.
It does. But what's even more interesting is when you look at the sub-benchmarks, like LIBERO-Long, which are tasks with many steps where errors can build up.
Error accumulation, yeah.
ACoT-VLA hits 96% there, compared to 92.4 for Pi 0.5. It's evidence that thinking in actions helps the robot stay on track over a longer horizon.
But the stat that really jumped out at me was on LIBERO-Plus. That's the really hard one, right? The robustness test.
That's the one. LIBERO-Plus is designed to break these models. They mess with the lighting, they jitter the camera, they randomize where the robot starts.
And ACoT-VLA got an 84.1% average success rate versus 75.7 for the next best.
And if you break that down, you see the story. On tasks with camera viewpoint shifts, ACoT-VLA had an 11% better success rate. With robot initial state changes, it was over 16% better.
Why is it so much better when the camera moves? That feels important.
It goes right back to the Semantic-Kinematic Gap. If your model is basically doing visual matching, Does the current image look like my goal image? And you move the camera, the pixel space is completely different. The model gets lost.
But if you're thinking in actions.
An action is geometric. Move your hand forward 30 centimeters is a command that's true no matter where the camera is.
Right. It's anchored in the physical world, not the pixel world.
Precisely. The EAR provides that geometric anchor. The motion plan stays consistent even if the visual input gets noisy. And that is a massive, massive advantage for sim to real, where your camera and lighting are never going to be perfect.
And speaking of the real world, they actually did this. They didn't just stay in simulation. They put this on an ACoT G1 humanoid and an Agilex mobile robot.
And, real world performance is always lower than sim, but the trend was exactly the same. They averaged about 66.7% success across a few tasks.
And how did the others do?
Pi 0.5 was at 61%, and the base Pi 0 was way down at 33.8.
And the pour water task looked like the real challenge.
Oh, fluid dynamics is the final boss of robotics. You have to grasp, move, tilt, pour at the right speed. It's a continuous control problem.
ACoT-VLA got 33% success there, which sounds low, but...
Yeah. It's a huge relative improvement over Pi 0.5, which was at 22%. It shows that thinking continuously in the action space is better for handling continuous physical phenomena like pouring. Text is discrete. Pouring isn't.
They also did some ablations, right, turning off parts of the system. And there was this weird finding with the ER module size.
Yes. The bigger is worse result, which is so counterintuitive in deep learning, where we're all taught that more parameters equals better performance.
Right.
But when they scaled up the Explicit Action Reasoner to be bigger than the final action head, performance actually got worse.
Why would a smarter planner be a bad thing?
The hypothesis is overfitting. If the planner is too powerful, it just starts memorizing exact trajectories from the training data. It stops producing a general, coarse, rough draft and tries to be too precise too early.
So you actually want the planner to be a little bit simple.
You want it to be a sketch artist, not a photocopier. You want a lightweight planner that provides a good general signal, which then forces the final action head to do the hard work of refining that sketch based on the live context. It keeps the whole system more flexible.
That is a fascinating takeaway for any ML engineers listening. Don't always assume a bigger component in your pipeline is better.
Structure matters more than scale sometimes.
So, zooming out, what do you think this paper really signals for the fields? We've had this big swing towards just pure end-to-end models, pixels in, actions out, total black box in the middle. This feels like a step back towards more structured, explicit architectures.
I'd call it learned structure. It's not old school hard-coded rules, but it's building an architectural bias into the model that says, hey, we know motion is fundamentally different from semantics, so let's give it its own dedicated machinery.
It's not throwing out the VLM brain, it's just giving it a dedicated motor cortex.
That's the perfect way to describe it. The ER and the IRR are the motor cortex. They're the translators that take the high-level intent from the LLM and turn it into the low-level language of the robot's body.
It makes me wonder what the next step for this action chain of thought is, because right now, the paper says the thought is just a sequence of joint angles. It's just a list of numbers.
Yes, it's raw kinematics. Move joint A by 5 degrees.
But if we're really taking this idea seriously, reasoning in the action space, why stop at kinematics? I mean, humans don't think in joint angles. We think in physics. We think about force and friction and momentum.
That is the logical next step, isn't it? What if the chain of thought wasn't just a geometric path, but an actual tiny physics simulation?
Exactly. Embedding a differentiable physics engine right into the reasoning loop.
So the model could hallucinate not just the path, but the forces involved. If I push with this much torque, the friction here will hold it. If you combine ACoT with an internal physics model, you could unlock some truly dynamic zero-shot skills.
Like a robot figuring out how to do a backflip or catch a ball it's never seen before just by running that physics thought loop a few times?
We are definitely not there yet, but ACoT-VLA feels like the first really big successful step away from what you could call the text trap. It's proof that for a machine to really move through our world, it needs its own native language of movement.
It needs to think with its body.
Precisely.
On that note, we'll wrap up this episode of AI Paper Podcasts. Really fascinating work from the team at Beihang and AGIBot. The link to the paper is in the description, as always. Thanks for listening.